for most of the problems which we will have to face on the way to a fusion reactor, and I'm confident that we will find solutions and they will be available within the next 20 or 30 years.
I give it about a 50-50 chance of success, and I would bet on that because we really are in trouble if we don't have satisfactory energy supplies in the next half of the next century.
This is no ordinary robot. It has been specially designed to refurbish the inside of this unique cavity. This cavity can hold hot gases at over 100 million degrees centigrade as part of one of the most ambitious research projects ever mounted. Just 15 kilometers from Oxford, Europe has come together to try to harness one of the most basic forms of energy, the energy which drives the sun itself, nuclear fusion. The project is called JET, and the JET experiment has been achieving new records in fusion performance.
10, 9, 8.
For scientists, the dream of an essentially unlimited supply of energy is providing one of the great challenges as we enter the new millennium.
I find it exciting working in a field that is trying to produce on Earth a limitless and safe source of energy.
JET has had the unique ability to put together many of the elements which will be required in a practical reactor system.
For beneath the veil of high technology lies an almost inexhaustible energy source with built-in environmental and safety advantages. What underlies the dream is that the fuel which powers such fusion reactions derives from the elements found in water. It is the fusing together of the isotopes of hydrogen, deuterium and tritium which releases the energy of the fusion process. Scientists and engineers from across Europe work closely together to tackle the problems which must be solved if fusion is to become an economic source of energy. One group is using the latest laser technology to look inside the fusion chamber and measure conditions such as the temperature. The laser beams down from a roof laboratory. The alignment of laser pulses is one of many checks before the real experiment gets underway. All the vast amounts of data are sorted, stored and analysed by computer specialists. The JET experiment is highly sophisticated and an adventure as exciting and focused as a space mission. What lies at the heart of the JET experiment is the aim of producing a stable plasma, which is a very hot gas of particles as exists in the sun and stars. This will be used to generate energy. One approach that has gone a long way to proving itself is to constrain the plasma in a torus or donut-shaped configuration. The plasma is held in place by powerful magnets. One problem is that it takes very little to destabilize the plasma. Creating and maintaining necessary plasma quality is a major scientific and technological challenge. The JET experiment is part of a long-term effort by Europe to harness its collective talent in fusion research. For inhabitants of the Earth in 50 years' time, interest in fusion today may be no idle curiosity. For choices may have to be made on energy sources by the next generation of crucial importance to the planet.
Can you see the transformer limbs and the orange steel around? You can see part of it.
To start producing useful fusion, the scientists of tomorrow will need to reach an important milestone in managing a plasma. Containing a plasma is not enough. The temperature has to be high enough. It must be dense enough. And the energy be kept in the plasma for long enough. This combination is called the triple product. If the triple product is large enough, the fusion reactions become self-sustaining. This key condition is called ignition. but it will be sufficient to produce a burning plasma short of ignition, so long as it produces enough excess energy.
Throughout the 1960s, scientists encountered instability problems while trying to control and heat plasmas to higher temperatures. The plasma would writhe like a maddened snake, breaking away from the magnetic grip.
But in 1968, the Russians reported a breakthrough with a torus of their own design they called a tokamak. They invited a team from Culham to come and check the claims. The team found that the tokamak could indeed grip the plasma more firmly and reach the critical 100 million degrees Celsius. This led some years later to the design of perhaps the most advanced tokamak ever built, the Jet Torus, brought about in the early 1980s by the combined efforts of the European community. As happens in science, this advance and the acceptance of the tokamak concept as the most promising way forward opened up a whole new vista of opportunity. In a sense, the story of the direct path towards practical fusion energy was only just beginning. The sun, which provides us with our light and heat on Earth, is powered continuously by nuclear fusion. This means that it must contain all the processes necessary not only to create fusion, but to maintain it. Yet we know that the sun is not in a peaceful, steady state. So what are the clues to help us here on Earth to create our own tiny suns?
To confine this hot gas, you need a force. In the sun, which is a very successful fusion reactor, the force is gravity. It is a very weak force, and it takes huge distances to hold the pressure of the sun. And of course, we have to do that on a device which is much smaller. And to do that, we need a much stronger force, and we use the electromagnetic force. A reactor condition demands that you have a hot core which reaches about 200 million degrees. And of course, if the gas would come into contact with the walls at this temperature, it would immediately cool down. It would probably not melt the walls because there is not that much energy in the gas. But certainly it would stop operation completely. This thermal insulation is measured by what we call confinement time. It's the time it takes for energy which you deposit in the core to actually reach the wall. In JET, we have reached a confinement time slightly in excess of 1 second. For reactor, you need to achieve between 2 and 4 seconds to reach the burn state.
In order to harness the energy in a plasma, it's necessary to know what happens at an atomic level. In a plasma, the individual particles are propelled around by their energy or temperature and the electric forces which exist between all charged particles. Usually, when two ions collide, they bounce off like billiard balls. But if the energy is high enough, they may interact or fuse. New particles are produced, and energy. It is the emission of the small particles called neutrons which generally provide the measure of successful fusion. At JET, the neutrons are counted, but in a power reactor, it is the energy of these neutrons that will be converted into electricity. But there is also a hidden bonus in a fusion plasma.
Well, in a fusion reactor, it actually will be the power produced by fusion reactions themselves which keep the plasma hot. In the reaction between deuterium and tritium, one of the products of that reaction is an alpha particle. That particle carries away 20% of the energy that's released in each fusion reaction. Because the alpha particle has a positive electric charge, it is confined by the magnetic field of the system. The alpha particle gives up its energy to the deuterium and the tritium ions and the electrons, thereby maintaining the temperature. And so, in principle, the process can become self-sustaining.
Anything else is changing?
One of the major achievements of JET has been to prove this key heating role of the alpha particles.
In the alpha particle heating experiment itself, what we were looking for was a rise in the plasma temperature attributable to the effect of alpha particle heating. We did that by doing a series of experiments, starting with pure deuterium, which has very low fusion reactivity, and scanning the mixture through the 50% level, which has the optimum power output, to 100% tritium, where the fusion power is very small. And we noticed that the maximum heating effect coincided with the mixture which produced the highest fusion power output. And in that way, we were able to decouple the effect of alpha particle heating from the possible effect of changes to the thermal insulation properties.
So, in a classic experiment, JET, using all its facilities, showed that the temperature rise had to come from heating by the alpha particles. This experiment could only have been done at JET because it alone uses deuterium and tritium as fuel. But there is no such thing as a free lunch in a fusion plasma. Ironically, this success in heating the plasma has a downside relating to its purity.
Now, the impurities come through two different mechanisms in a tokamak. The first one is because fusion reactions produce alpha particles, and after the alpha particles have collided several times with the plasma to transfer the energy, they will lose their energy and sort of slow down and remain in the plasma and dilute the deuterium-tritium fuel, which is necessary for the fusion reactions. Unfortunately, you cannot get rid of all the impurities that you produce, which is what ideally one would like to do. So what we have to do is to try and keep impurity production to its absolute minimum. And that's why JET operates with a diverter as well as other tokamaks in the world. And the main idea behind the diverter concept is to try and separate the core plasma, which is hot, from the edge, which is cold.
This outer region is where the alpha particle waste, together with impurities knocked off the vessel walls, congregate. So how is this separated off?
This separation is achieved by creating a magnetic separatrix inside the vessel, just by having additional magnetic coils, which actually diverts the edge plasma from the core and sort of flushes it away from it through a separate chamber that we call the diverter, which is placed at the bottom of the machine.
Each new shape of diverter was tested in a full fusion experiment. A key run took place in 1996.
All ready? Beams ready?
Each plasma lasts for less than a minute. The leaders of each session must adjust the magnetic fields and the injection of new plasma in the search for improvement. It's a trip into the unknown.
So now we're in the last 30 seconds of countdown. That's quite a pulse, isn't it?
The results of every run are analysed and stored. Each team looks for clues in its own apparatus as to how the plasma is behaving with the new diverter.
And which is the bigger anyway? The 1 to 10 is larger, horizontal. That's the way around it was.
The way a plasma dances to the orchestrating magnetic fields is one of the key pieces of physics now being unravelled with the diverter present. It will dictate the success of future machines.
The plasma, this hot gas, which we call plasma, is a bit like an unruly crowd. It tends to go where you don't want it to go in very sudden fashion. So much of our research has been to study the condition under which the plasma is stable. JET has demonstrated, for instance, that it's possible to have very good confinement, very good insulation, both at the edge of the plasma and in the plasma core. And that has allowed JET to reach record fusion performance.
As the power was increased, JET scientists and engineers waited for the signs that the plasma was producing a new record in controlled fusion energy. By late 1997, a pulse of more than 16 megawatts of fusion power had been achieved for the first time in a controlled fusion experiment. The aim now is to scale up fusion experiments to reach the all-important stage where the plasma can be heated sufficiently by its own alpha particles so that the temperature is maintained with little extra heating. So how has JET pointed the way? Progress has been made at JET on all three factors needed in the so-called triple product: the density, confinement time, and the temperature. Each has been achieved separately to a level necessary for a reactor. That is, good enough density, a temperature of over 300 million degrees exploiting JET's powerful heating systems, and a confinement time of more than 1 second, possible through JET's size and operating concepts. A clue to the nature of the next challenge, combining the three conditions, comes from the secrets which a plasma is still revealing on its crowd-like behavior.
Plasmas have similar characteristics. They tend to flip into a mode or another mode. And this has been one of the most exciting things for a physicist, which is to discover these modes. And many of them were unexpected and came as a surprise. So we have essentially discovered three main modes. One which is the ordinary one, which we call L mode. Then came the H mode, which was discovered on the German machine called ASDEX, which has a confinement barrier at the edge of the plasma. And that improved the performance by at least a factor of 2. And then more recently, and this was done in JET, we discovered what we call the PEP mode, which is our jargon to describe that there was now a confinement barrier which was well in the core. And we also discovered that you could combine the two and benefit from both sides. And so we are further improving now on these concepts to make the best use of the magnetic field that we have.
What makes these patterns or modes of behavior in a plasma so important is that they can provide ways of slowing down the outward drift of particles and energy which limit the fusion process. In the ordinary mode, the heat and particles drift steadily towards the outside. In the so-called H mode, the drift is slowed quite significantly as the outer areas of the plasma are reached, keeping the energy in the plasma for longer. And in what is termed the PEP mode, there are zones within the plasma which slow down a migrant particle. This increases the energy confinement time and improves greatly the fusion performance. A reminder of the tiny quantities of fuel needed for fusion power came as samples were unloaded in preparation for the big run. This canister contains just a few grams of tritium. In a real power station, just 1 gram of deuterium and tritium as fuel would replace 10 million grams of coal or oil. Also, the daily waste from such a 1,000 megawatt plant would be just 2 kilograms of helium for a fusion plant, compared to some 30 million kilograms of carbon dioxide, sulfur dioxide, and other wastes from a fossil fuel plant. Humanity has shown that it can take on ambitious challenges if it feels they are worthwhile. The space program is an obvious example. But for only a fraction of the cost of the space program, huge strides forward could be made in developing practical fusion energy in a cause which may become critical in the second half of the 21st century.
We need a machine roughly twice the size of JET, or perhaps slightly more. And this is in order to achieve confinement times which allow the alpha particle to maintain the heat in the plasma. Such a machine would allow also, of course, to demonstrate fusion power production at the level of the gigawatt. At present, we are doing our research essentially one step at a time. We solve one question and then we process to the next. With a larger budget, we could essentially progress on 3 fronts. We could progress on the physics of what we call burning plasmas or ignited plasmas, which I already talked about. We could progress on material and technology. And a third aspect would be to research on concept improvement.
For fusion scientists, concept improvement means looking for new plasma modes, new ways in which a plasma might maintain fusion more effectively. This is an exciting prospect. There are also some key practical questions which an increase in scale will raise.
It's clear that one of the problems that future plasma experiments will have to face is that of the lifetime of the diverter. At present, the regime that looks more promising for the operation of the reactor, it produces large bursts of energy that land very fast on the diverter components. And now these bursts of energy produce very high heat loads. And if you were to scale these heat loads to larger tokamaks like a future reactor, that would produce very high levels of erosion, and the diverter couldn't last very long. So it's clear that this is one of the challenges that JET, together with the fusion community, has to address now.
You need materials which don't contaminate the plasma, which can resist very high temperatures, and which can also resist a flux of neutrons. So these materials have been identified, they exist, but they need to be qualified in the real situation.
The dilemma at the heart of fusion research is that if fusion energy is to be available in 50 years' time, when it will be needed, decisions have to be made even while oil and gas are still plentiful. But the foundations for making a clear leap forward have been laid at JET, where systems for heating up the plasma to over 200 million degrees, for recycling the tritium fuel, and for maintaining a fusion plant remotely have provided a successful framework to test many of the other elements needed to enhance the fusion process.
At JET, basically, we've been able to show that fusion works and we can make fusion reactions. What we have to do in the future is to build a bigger experiment and actually show that we can generate electricity on a commercial scale.
I think JET has produced a very good model for the next generation of tokamak experiments. And in fact, JET has fulfilled all the aims that were set 20 years ago when it was designed. And in particular, and amongst others, JET has demonstrated alpha heating and helium removal in a design that is the closest to that of a reactor.
However history comes to place the JET experiment, one thing is sure. Without such steps into the unknown, humanity may never have a chance to benefit from a potentially limitless fuel. A fuel perhaps cast to the needs of a new millennium.